So we are discussing about the induced voltage in a coil when it is placed in a sinusoidally varying flux density distribution in space. That is, B distribution along the space angle of the machine is sinusoidal. That is, this is B, this is theta, where theta is space angle in electrical, and this is B max. This is B max. Just I will quickly go through what we did last time. And if the relative speed between the field and the coil is n rps mechanical, then the induced voltage in the coil will be root 2 pi into Pn by 2 into phi into n. Pn by 2 is the electrical speed of the relative speed expressed in electrical rotation per second, relative speed in rps. So it will be root 2 pi f phi into n. P is the number of poles of the machine, and phi, remember, it is flux per pole, and that is the flux under each pole. If you calculate B d theta integrated over 0 to pi, of course, remembering that d theta should be expressed in mechanical degree because area is mechanical. So that one we did last time. And R is the radius of the air gap of the machine. So air gap is so small, the radius of the conductor of rotor and stator can be taken to be approximately equal. So wherever that conductor is placed, that radius this is the radius. Okay. So this was the expression for the voltage expression in a single machine. Remember that this is similar to that of a transformer, and this is the value of the RMS voltage, you should remember. Because in a transformer also the voltage induced is root 2 pi f. Of course there it was phi max into n. Now this is the one of the simplest problem. Now the next problem, what I was telling, if instead of a single coil, if there are 2-3 coils which are distributed in space, how to calculate the induced voltage? For example, so voltage across more coils distributed in space. The problem basically means that suppose if you have instead of a single coil, this time I am not going to draw these slots. Suppose this is one coil which is multi-turn coil. This is one coil having n number of turns, and you have got another coil. Say this is another coil, red, which is also n number of turns, and you have got another coil which is also having n number of turns. But there, what I will assume is this: they are distributed in space by equal angle, that is beta. The angle between the coils are beta, and these coils are kept in a magnetic field which is sinusoidally distributed in space, and I want to find out what will be the resultant voltage if the coils are connected in series. To find out the resultant voltage. When the coils are connected in series. We can name the coils also like this. Suppose this is a 1 dashed, this is a 2 dashed, 2 dashed, let us call it 2 dashed, and this is 3 dashed. obviously the induced voltage in the individual coils will be like this, given by this expression. So the magnitude, the voltage in each coil has a magnitude, has same magnitude and given by E coil is this one, root 2 pi f phi into n. However, they will differ in phases, which can be easily seen. Suppose the relative speed, the resultant field, suppose this is the resultant field. I am just drawing by an arrow. Suppose this is the resultant field. And relative to this set of coils, it is moving in this direction with a speed n mechanical RPS. Then as you can see, whatever happens so far as the flux linkage is concerned in coil 1 now, it will happen in coil 2 after an angle of beta, and in coil 3 after another angle of beta. Therefore, the voltage induced in 2 will lag voltage 1 by an angle beta, and voltage induced in coil 3 will further lag by another angle beta. Therefore, you have to add now 3 phasors whose lengths are equal and they are displaced by angle beta. So, this will look like suppose I call this voltage to be voltage in coil 1, E1, this phasor. The voltage in coil 2 will have equal length, but will be lagging this one by this angle beta, lagging this voltage by an angle beta. Lengths of course are equal, and this is, suppose the phasor representation is E2 bar, and finally you will have the third coil induced voltage which will be lagging E2 by further another angle beta, and this voltage will be of course E3 bar. Our problem is to find out this resultant voltage. This is, I will call it E resultant. How much it will be? Okay. Now to do this, what I will do, you see that this length being equal and displaced equally by equal angles from each other, therefore they will form they are the sides of a regular polygon. So you can draw a circle which will pass through the corners of this polygon. Suppose the center of that circle be here. Are you getting? You can draw a circle which will pass through the corners of this polygon. It is a regular polygon. Suppose the center of that circle is O here. Now what you do, you join these corners with this center here. Then what will be this angle? These angles will be how much? They will be also beta. You can easily show. This is the outside angle. It is a regular polygon. So these angles also will be beta. Beta here, beta here, beta here. Okay. And what is the length of each coil? Length of each coil, that is the magnitude of E1 bar. You remember we did earlier, E1 bar, length of E2 bar and length of E3 bar are same, and we are calling it to be E coil, that I wrote earlier, the magnitude of this one. Therefore, suppose the radius of this circle or of this side is, suppose R. R is this radius here. Now what you do, this is just a one line proof. What you do, from this one you drop a perpendicular on this vector. So this angle will be then beta by 2, beta by 2. This 2 will be beta by 2. Then in terms of this radius r, this E coil, this length is E coil. So E coil will be how much? E coil will be twice r sine beta by 2. That is, this is 90 degrees. So r sine beta by 2, twice of that is E coil. This will get. Similarly, what you do, you drop a perpendicular on this red line from this center. The resultant voltage, E resultant, the magnitude of the E resultant will be how much? This angle will be how much? 3 beta by 2. 3 beta is the total angle. It will, I have dropped a perpendicular, so 3 beta by 2. So this angle, that is this angle, is 3 beta by 2. So this is also 3 beta by 2. So this will be twice r sine of 3 beta by 2. Now what you do, you take the ratio of these two, E resultant by E coil will be simply sine 3 beta by 2 divided by sine beta by 2. Okay. Now what you do, you multiply both sides by 1/3. Then this will be E resultant, that is E resultant by 3 E coil will be equal to sine 3 beta by 2 divided by 3 sine beta by 2. Okay. Now left hand side, let us see, what do you think this 3 coil is? 3 coil is, if the coils were not distributed in space, if they are placed in same place, you getting? You have got 3 coils, separate multi-turn coil. Each one of them is having n turns. Here how I have placed one coil like this, one coil like this. This is having multi-turn in the same place like this. Second coil also may have several turns, same number of turns. And here also another coil, 3 turns, but they are distributed in space. But suppose all these 3 coils were concentrated in a pair of slots, then what would have been the induced voltage? And if these coils were connected in series, that is, in this case, what I would have done, suppose in a non-distributed coil, this is suppose coil 1, 1 dashed, 2 also you place here, 2 dashed, 3 dashed. That is, I have not suppose distributed the coils. I could also connect 3 individual coils in the same place, same pair of slots. Then what will be the resultant voltage if the coils were connected in series? Then the voltage induced in coil 1, 2 and 3 would have been in same phase, and your addition of these vectors would have been this plus this plus this. So what would have been the resultant voltage? 3 E coil. So 3 times E coil is what? Is the voltage that one would have got if the coils were not distributed in space but were concentrated in a pair of slots. And what is this E resultant? E resultant is the voltage if the coils are distributed in space by same angles beta beta like that. Are you getting? Now this E resultant, let us calculate like this. this E resultant will be equal to, let this factor, I will tell you why it is called, so this factor is called distribution factor. And obviously, because of distribution of the coils, E resultant obtained will be less or more than when the coils were not distributed. This length is obviously less than sum of these three sides. This side is less than sum of these three sides. Therefore, because of distribution, you sacrifice something. The voltage available becomes lesser. Now, by what factor it is less compared to the case when the coils were not distributed is known as distribution factor. Okay. So, distribution factor is this one, Kd. That is, E resultant is Kd into 3E coil. That is, the moment you distribute the coils, you get lesser voltage, like that. Now, as a general case, if instead of 3 coils, if you imagine if m identical coils, having each having n turns are distributed in space, such that the angle between the consecutive coils is beta electrical, then what would have been the value of Kd? Kd would have been, for 3 it would have been m. Suppose there are instead of 3 coils, m coils. So that by putting, so it would have been sin m beta by 2 divided by m sin beta by 2. This would have been the distribution factor. So now I will write, see how easily I will write now the expression for the induced voltage of the resultant. It will be like this, E resultant. You do it like this. E resultant would be root 2 pi f, phi is flux per pole. Now come to number of turns. Actually, there are 3 coils, each are having n number of turns. So 3n should be there, each having n number of turns. But if I write only 3n, shall I be wrong or correct? For distributed coil, this would have been 3n, provided all the coils were concentrated. Now, series in both the cases, but had the coils been concentrated in same pair of slots. Now you have to multiply with Kd. That is, by this factor induced voltage gets reduced. Or in other words, sometimes it is written like this, root 2 pi f phi, that is as if effective number of turns has decreased. So effective number of turns is n effective. So the moment you distribute the coils, as if effective number of turns are decreased. In case of transformer, there was no problem. Transformer, this was the limb, all the turns were like this. They were linking the flux in same phases, d phi dt same for all of them. There was no question of distribution. But here in rotating machine, if you want to utilize whole of the periphery of the machines, because you have to put conductors, otherwise suppose you select a big, large diameter machine and only one coil you put, other places remain unutilized like that. So you are forced to use distributed coils. And the moment you do that, of course, effective number of turns will be less by a factor, which is called the distribution factor. So voltage induced in a coil gets slightly reduced. Now there is another factor which can also reduce the effective number of turns, and that is called the pitch factor. This I will tell you. Pitch factor. So far I have told you the span of the coil should be how much? 180 degree electrical. 180 degree electrical always, because you can maximize voltage like that. And also you have seen that I have assumed one thing: when there is a coil, full pitched coil, it carries current. What is the MMF distribution? Suppose it carries direct current. MMF distribution is what kind? Single coil, rectangular. What is the type of MMF distribution? It is rectangular in nature, is not? And I am considering only the fundamental component. So there will be induced voltage because of other harmonics also present, that we have neglected so far. Now what I am trying to tell, sometimes, I mean, you may ask like this: suppose, okay, without bothering those things, suppose I have a coil like this. Let us put the problem in this way. This is a machine. This is, suppose, the B distribution stationary in space. Rotor is rotating. Generally, how I am putting the coils, full pitched coils, here one coil side, the other coil side should be here. That is what so far I was telling you. Now suppose, just as an academic exercise, I ask you, somebody has put the other coil side not here. He has put slightly here. This is 1, this is 2. Suppose instead of putting a coil, full 180 degree span coil, suppose he has used a coil span equal to, say, 170 degree, 10 degree less. Will there be induced voltage? So what will be the induced voltage across the coil? I want to find out. Suppose, let us not go into those why it is used right now. Just I give as a problem. Suppose instead of putting one coil side 180 degree electrical apart from the first coil side, somebody has put by some angle other than 180 degree. Then what will be the induced voltage in that single coil? I want to find out. I will tell you when, under what conditions these types of coil may be used. But suppose I want to calculate that voltage induced. I will put it first like that. So how will you do it? This is also very simple, not very difficult, because of the fact, see, if you look from this one, this is the coil 1 here, and the other coil side is there, and this span is other than 180 degree. Suppose what I will tell is the angle by which it is less than 180 degree, that I call epsilon. So what is the coil span now? 180 degree minus epsilon, pi minus epsilon. It is like this. Now this coil is joined at the back, because it is a coil after all. It will have its return path. And I will call this side A, B, this side suppose C, D, like this. And you imagine a magnetic field is traveling like this, perpendicular to this B distribution, relative speed. Let us assume this is stationary. A flux distribution is moving from left to right. So I want to find out the resultant voltage between D and B. Now suppose at this one, now this individual conductor becomes a source of EMF. BLV is there, BLV is there. Now suppose at any point of time, this AB is under the center of north pole. Maximum voltage will be induced. and suppose the field, coil is moving in this direction, field is stationary, you can find out the polarity. Suppose this becomes plus, this becomes minus. Now what I will do is this voltage phasor at that time, suppose this is the voltage phasor, E potential of A with respect to B, this is the phasor. Now the same thing will happen to the conductor CD after 180 degree minus epsilon, that's all, the same level of flux density. So where will be the phasor E bar CD? E bar CD will be after, say this is 180 degree, so below this angle is epsilon, then E bar CD must be there, E bar CD, remember, this double notation is important, E bar CD will be here. The potential of C with respect to D, the same thing will happen after 180 degree. Then I want to find out EdB, E bar dB, E bar dB. So you start from this one. So this voltage and this plus, this is also plus. So you have to subtract this one. So this resultant voltage will be across dB E bar AB, E bar AB, minus of E bar CD, E bar CD, where this angle is epsilon. So minus of E bar CD if you do, and you will get the resultant voltage. If the coil span were 180 degree, then this plus this, just algebraic sum, that twice BLV you would have got. Is that clear? So this addition of these two things will give you the voltage. And in terms of this one, the induced voltage in the coil, if the coil span, if this coil span were 180 degree, suppose this length is the conductor voltage, each conductor voltage. So you write, if the coil span, if the coil span were 180 degree, and such a coil are incidentally called full pitched coil, full pitched coil. Then what would have been the induced voltage across the coil? 2 times the conductor voltage. So this is E conductor, E coil side I say, E coil side, the magnitude. This is also E coil side, magnitude, E coil side. So this would have been equal to then voltage across the coil, voltage across the coil would have been twice E conductor, coil side. But now what will be the voltage? This is E coil side. Length is E coil side. This is also E coil side. This angle is epsilon, and this is the resultant voltage. So this is epsilon by 2. This is also epsilon by 2. So this will be if coil span is equal to 180 degree minus epsilon, electrical, all are electrical. Then the induced voltage would have been twice, that is this projection if you take E coil side, cosine epsilon by 2, that's all. This projection and also this projection, this total length E resultant. Therefore, your voltage would have been reduced by a factor of cosine epsilon by 2, where epsilon you write down is called epsilon, this angle epsilon is called the angle by which a coil is short pitched. Therefore, pitch factor which is denoted by Kp is cosine epsilon by 2, and pitch factor obviously will become 1 if coil is full pitched, because epsilon is 0 in that case. Okay. Therefore, these are the two factors. Therefore, if a three-phase coil or any winding coil, single phase also, suppose the coil is both distributed and short pitched coils are used instead of full pitched, then effective number of turns should be multiplied by both Kp and Kd. See, in general, if a winding is both distributed and uses short pitched coil, the effective number of turns will be Kp Kd into n total actual turns. This product Kp into Kd is sometimes called the winding factors. Kw it is called winding factor in actual, where Kw is Kp into Kd is called the winding factors. Why the coils are short pitched, I will tell you later. Let us not go into detail. But suppose the windings are both short pitched and use as distributed coil, then fundamentally what I want to tell after doing all these things, that in a three-phase machine, the induced voltage in a winding coil for a particular phase, I should write it like this: √2 pi f flux per pole into Kw into actual number of turns which are connected in series. So this is the difference with a transformer thing. There comes another winding factor. This you should remember. Now, so far, of course, I will right now here point out in our say distributed coil, a simple distributed coil, three-phase distributed coil. Let us go to that winding. You just go through that. I will not draw, but I will tell you one thing. Say two-pole configuration. This was R1, R2 I placed like this, is not? Then Y1, you just listen. Y1, Y2 I placed like this. And B1, B2 were placed like this. Suppose there is a magnetic field moving here relative to these coils, then there will be induced voltage in R1, R2. But here, do you think I should take into account Kw? Kw is 1 here, because there is a single coil in R phase there, and B phase also there is a single coil. Now, in actual three-phase winding, which I will take up after few lectures, you will find even the R-phase coils will be distributed in space. R-phase winding instead of a single coil, which is a very simple diagram. In no machines, three-phase large machines, you will find only a single coil in R-phase. There will be several coils which will be separated by equal angle like beta and connected in series will make an R-phase. Similarly, for Y-phase, everything will start after 120 degree and will have several coils which are distributed in space, like that. So there I have to take that angle into account and calculate the effective number of turns. This you just keep in mind. I will once again point out when I will take somewhat a realistic winding of three-phase machines. But with this background, I can now start induction machine. So in rotating machines, you should remember the actual number of turns physically, whatever you count, that alone will not be in this expression. It should be properly corrected because of distribution of the coils. Now let us come to induction motor, three-phase induction motor to be precise. So on the stator of a three-phase induction motor, a balanced three-phase distributed winding, balanced three-phase distributed winding. So stator consists of a balanced three-phase distributed winding on the stator. The type of winding I discussed earlier. Now rotor may be of different types, but to begin with I will assume that rotor also houses a balanced three-phase distributed winding. Therefore, both stator and rotor houses two balanced three-phase distributed winding. At least to begin with, I will. There are other types of rotor. Other type I will take up at appropriate time. Other type possible. Just keep a note of this one. Now, to tell you the theory, what happens therefore, I should not draw all the detailed diagram now. I will symbolically now represent it like this. On the stator, you have got a balanced three-phase winding, which may be star or delta connected and fed from a balanced three-phase supply. So I have taken star connection. And on the rotor, also as I told you, I have a three-phase distributed coil. I'm sorry. This is on the rotor. And of course, rotor terminals should be accessed from, how? Rotor terminals should be accessed? Slip ring and brushes. So there will be, suppose, 3 slip rings. 3 slip rings are there. One is here, another is there, another is there. And there are 3 brushes, fixed brushes, which are there. And the stator terminals, these blue ones, I will give a 3-phase supply. Three-phase supply you give. You give 3-phase supply. And suppose initially the machine was stationary, nothing was in motion. Therefore, the moment you give 3-phase supply to the stator, what will result in the stator? A rotating magnetic field will result. It will draw balanced 3-phase current, and a rotating magnetic field will result. Suppose I will denote it like this. Of course, not every time I will draw like this. So a rotating field result produced by the stator. So this field I am calling Fs. And what will be its speed? Its speed will be, I will write mechanical speed if I write. I will write it Ns 2F by P. So much of RPS. This you remember, mechanical speed I have written. Or its speed will be F, electrical. So much F rotation per second, or you say 2F by P rotations per second in mechanical terms. That is, if you could measure with a tachometer. Of course, it is not possible to measure the speed of a field by tachometer. That understanding, that mechanical speed I am talking. So, such a field will be produced. Now, this field, I will draw slightly. So, this is the stator. This is the stator. And now there is a field produced. Fs, which moves with a speed ns mechanical. And another thing I should write, what I should write? With respect to what? So I will write with respect to what? Stator, because the winding is housed on a stator, or with respect to a stationary observer. They are same thing. With respect to stator or stationary observer. So this is connected there. Now on the rotor, you have got this three-phase winding, which is not rotating, and these terminals are, I will not draw these slip rings all the time. So these are the rotor terminals. Suppose they are kept open. Now you tell me what is going to happen. Three-phase supply. This field will link both the primary windings. Therefore, there will be induced voltage in the primary windings. The stator windings, there will be induced voltage like a transformer, and also they will link the rotor terminals as it moves. So there will be induced voltage in these phases, and balanced three-phase voltage will be induced in the rotor, because rotor is also a balanced three-phase winding. So while winding, I have taken into account the Y phase is 120 degree apart in space like that. Therefore, there will be these coils on the secondary too will become a seat of EMF. If you neglect, like transformer, the ideal, no resistance, leakage flux, etc., then there will be induced voltage in the stator. Suppose per phase, I will call it E1. Per phase induced voltage, what will be the expression? Root 2 pi F, flux per pole is phi. What is flux per pole? Whatever this field B is distributed, area under this pole. So root 2 pi F phi into, suppose N1 is the turns per phase physically, so I should write some KW1 into N1, where KW1 is the winding factors of the stator winding. Similarly, if N2 is the rotor number of turns per phase, therefore there will be induced voltage in each of the rotor, RMS value of which will be E2 is equal to root 2 pi F phi into KW to N2. What is N1? N1 is the number of turns per phase of the stator, actual number of turns. Per phase in stator. And what is N2? N2 is the actual number of turns per phase in rotor. And KW1 I am not writing, and KW2 are the respective winding factors of stator and rotor windings. Now what I am trying to tell, if you take a voltmeter, if you measure voltage across the rotor terminals here, or here, you will measure this voltage. Similarly, if you take a voltmeter here, if you measure, you will measure the primary applied voltage per phase. So, what is the ratio of these two voltages, induced voltages? N2 by N1, I mean effective number of turns ratio, that is magnitude of E2 by magnitude of E1 will be equal to Kw2 N2 by Kw1 N1. That is ratio of effective number of turns, just like transformer. This is primary, this is secondary. When rotor terminals are opened, you have not connected anything on the rotor terminals. So perhaps one may think I can get it is a kind of transformer where you can supply the load from these rotor terminals. In fact, there are transformers which are called induction regulator, where rotor is not allowed to rotate and it is supplied from voltage, that is there. So this is when rotor terminals are open, rotor open. Okay, I will just today have enough time just to tell this much. Now suppose this three-phase supply on the stator I am going to give, just I will ask you also to think in these three terminals. Suppose I keep shorted, and initially the machine was stationary. Rotor speed, I will denote NR as rotor speed, mechanical rotor speed, mechanical. Stator produces field, Fs, moving in this direction, Ns. So initially, when supply is given to stator, NR was 0, and it is kept shorted, rotor terminals shorted. Now, what is going to happen at t equal to 0 plus? You switch on the supply. A rotating field will develop. It will induce voltage here. But now rotor terminals are closed. Therefore, there will be some currents here. Three-phase currents will be flowing. Now, these rotor conductors, if you compare with the previous case, there were rotor conductors. They are not carrying current, and it was placed in a magnetic field. So there was no question of any torque production on the rotor conductors, because you require B, I, L is there, but I was 0. But now it may appear that rotor is carrying current, and it is already placed in a magnetic field, so it should experience some force or torque. Anyway, this aspect I will take tomorrow. So today I stop.